final installment from Jim today. Okay, so take it away.
Okay, so this is going to be the thing that we built up to over the last few lectures. And it's going to be entertaining only because I tried to hint to you all the little features that are going to show up. I can't say the calculation is exciting all by itself, but the fact that it shows, hey, there's a crossover, hey, there's a singular correction to scaling, hey, things like that, I'm hoping that it will help. And also, we've heard lots of people talk about jamming and how jamming the moduli go to 0, and there's a huge density of states, and all of that will come out too. But if I haven't convinced you to care about universal scaling functions, it's going to seem a little dry. So I'll do my best to act enthusiastic so that you have an excuse to. So today we're going to roughly recapitulate the Curie-Weiss law mean field theory that we did earlier, which describes not only the magnetization in zero field, but the way the magnetization rounds out when you add a field. Okay, and we did that in 4 steps, and I'll talk about the 4 steps, 0 to 3, just before I get to it, so we don't have to read the board right yet, if you don't mind, if you don't care. And the new theory is going to describe both this jamming transition where spheres gradually get squished together until they reach the isostatic point at which each sphere in 2 dimensions has 4 neighbors, and in 3 dimensions would have 6 neighbors, where the number of constraints equals the number of degrees of freedom. And it will also describe this rigidity percolation transition, or any rigidity percolation transition we claim that's isotropic. Now you'd look at this and you say, there are these hexagons and triangles, it's not isotropic, and I have to admit, it's not isotropic. That's a big barrier, and we're going to address that. Okay, so we're going to have a jamming theory, a rigidity percolation theory. We're going to have the jamming theory will have a universal scaling function, which inside it, just as the fracture problem we had, is going to have a rigidity percolation transition branching out of it. All right? So the original calculation done by Danilo Liarte, Tom Lubensky, Olaf Steno, and Xiaoming Mao was on this rather complicated lattice with hexagons and second neighbor triangles. And you can think of it, though, as one of a number of these calculations where you take some bonds, here's a triangular lattice, and you try to mimic the diluted lattice, one of these guys, by a pure lattice with weaker bonds, with weaker frequency-dependent bonds. As I was telling you before, if we can get a frequency-dependent elastic constant, we should be able to reiterate all the properties of the material. And these frequency-dependent bonds will be produced by writing the weak lattice as a sum of P, the probability of a given bond being in the lattice, times the weak bonds surrounding by the original frequency-independent stiff bond, plus 1 minus P, the fraction of no bonds, times a lattice without a bond. Now, you can sort of see how to do this elastically, but we also want the frequency dependence. And so this calculation is going to involve thinking about all the different phonons and how they scatter off of this strong bond and this weak bond, and reassembling it into a self-consistent relation. So the CPA replaces the lattice with K1, filled with probability P, with an effective weaker lattice with a complex Kp of omega. The imaginary part of this Kp of omega represents the fact that if I have a wave coming with a certain frequency through the lattice, it'll scatter off of this vacancy or this stiff bond and won't be the same wave you started with. And that will be like dissipation. That will be like getting the damping of the phonon mode, the damping of that vibrational mode. And that damping, that integral over all possible phonons in the Brillouin zone is going to be part of the calculation that we do and that they did. So you replace a random lattice with a spring K1 with probability P with a complex Kp of omega. You include the self-consistent effects on all the phonons. The new bond is weaker by Kp of omega over K1, which is going to be P minus a function H divided by 1 minus H. There was some initial thought that Tom would add to his infinite number of other things he talked about this self-consistent calculation. He didn't, and I'm not going to try because I just admire the paper without actually spending much time figuring out why it's P minus H over 1 minus H. Although Danilo tried to explain it to me, and I didn't have time to absorb it. So H of omega then will be 1 over the coordination number divided by 2. I don't understand why we have Z being the number of constraints per atom and everyone else has it being the coordination number, but whatever. Z, and then you integrate over the Brillouin zone to the trace of the dynamical matrix, which I introduced a few times. Tom introduced and then I talked about briefly, times the Green's function. The Green's function telling you how it would go bouncing around in this lattice, the dynamical matrix telling you the energy, and somehow this takes that fraction P of bonds and figures out a self-consistent relation which is given by this integral. Now, dynamical matrix Green's function, so these guys are written in terms of K of omega. Okay, that's what makes it a self-consistent thing. K of omega is complex, the imaginary part is damping, we said that, energy is conserved, and the damping has plane waves bouncing off of the dirt. Questions? This is not what we're going to do. Yeah.
I'm just wondering why is the part with the Kp of omega, why is this dissipation part it's imaginary?
So this is a standard picture that I suspect when I start writing it down, you'll say, oh yeah, I remember that, right? That you have a force which looks like this, and you would think that your acceleration F equals ma would be in phase. This is the acceleration. But it's not always in phase. If I have F equals gamma v, that's damped, then the acceleration is shifted to, I don't know, something like this. And so if you write the f of omega equals k over m x of omega, and then you have e to the I kx, and k has to have an imaginary part, real part of k, imaginary part of k. So this phase is producing a not just a real function multiplying this force e to the, so this is not cosine sine anymore, it's e to the I k t, I omega t. I'm improvising. E to the I omega t, this is a real part of k, e to the I omega t. We have 1 over a real part of k. And this is the imaginary part of k, gives you the out of phase response. Gives you a lag. Other questions? Again, if you don't ask questions, we'll all fall asleep, and I will finish very quickly. Okay.
Could you repeat what do we get, like, what is the motivation behind the self-consistent relationship? What are we trying to find from this?
We're trying to find k of omega here.
I see.
Okay? Or in this case, since we have nearest neighbor bonds and next neighbor bonds, we want K1, Kp, and Kb, the two kinds of bonds of omega. And when we do it, we're going to want lambda of omega and mu of omega. Yeah?
How do we know what kind of lattice to choose?
So these people were very clever. Normally, you try a lattice and you're interested in some lattice. The triangular lattice was done long, long, long ago, so you can't keep writing papers on that. So you have to convince yourself that the twisted Kagome lattice has some interesting property. This case, they carefully picked one lattice which had a bulk modulus and no shear modulus, because they wanted the bulk modulus to jump as soon as they took a bond away. And then the other lattice was just convenient triangular lattice. And that allowed them to get a jamming transition if they carefully didn't take out any of the one kind of bond. And I think that's how they motivated it, or you motivated it, right? Yeah. Oh, rough. Yeah.
I don't understand
Then it goes floppy, yes.
You get damping when you remove bonds. I mean, why that happens?
You get, well, first of all, it becomes floppy, but if I put any kind of impurity in a crystal, then phonons coming in will get scattered, and that will cause acoustic attenuation. Exactly. And this is just one kind of bond. And the cool thing is that you can calculate that pretty well, even for impurities in metals and things like that, or in silicon, by using this exactly the same kind of CPA, if I understand it right. So this is, again, in the Anderson paradigm, this is trying to make the jamming transition look like an ordinary boring material, except you modify the boring material a little bit by making it a frequency-dependent elastic constant. Okay. This is they can do the lattice calculation. Every time you take another data point, Stephen has to do an entire integral over this hexagonal Brillouin zone. That's even for the triangular lattice. For that other lattice, it was a pretty messy calculation. And he implemented all that, and we started saying, okay, we wanted the universal scaling function, and that was going to be the small q, small omega limit of all of these self-consistent integrals. And we could see that it was doing a nice job. And in fact, Danilo had told us the answer, and we could see it in the answer. And we were trying to do it again. I've forgotten why we were trying to do it again. But we couldn't get the formulas to give good answers because it was a lattice, and jamming is isotropic. And we knew that the answer was going to be the isotropic piece, so up to q squared we could do it, and we got rigidity percolation. But to do jamming, we needed q to the fourth terms, and the q to the fourth terms were already anisotropic. And we couldn't figure it out. And we finally said, there's no particular reason why we needed to start with a lattice. Let's pretend we were clever and could take an isotropic, weakened, frequency-dependent elastic material and treat it as P times something with a circular plug of rigid material plus 1 minus P times a circular hole. And we'll just do the same thing, okay? And of course, we still need two kinds of holes. So one of these holes is going to make lambda equals 0, and the other kind of hole is going to make mu equals 0. You could imagine. And I encouraged Stephen just to say, well, we're going to just have the same equations we had before with the same integral, with the same 1 minus p over p minus lambda over 1 minus lambda and p minus mu over 1 minus mu. But here we're going to not integrate over the Brillouin zone. We're going to decide the Brillouin zone is circular so as to not have any anisotropy. So this is called the Debye frequency, and it's an approximation. But for us, we call it the Debye frequency, but it's just a number that we use to make a lattice constant in it. All right?
What Z means now? What Z means? It's not coordination anymore.
Z we left in because we didn't know what to call it. And in fact, one of the Z's happens to be 1, and there's an argument for that that I never did follow, but it's in the paper. It's in the notes that are going to eventually be a paper. This is very new. This is very new. And still, some of it isn't quite worked out. But all the stuff I'm telling you, 2 dimensions is a crucial thing that we want to get done. But, okay? So, now remember the dynamical matrix and the Green's function. You may not have remembered, but this is in 3 dimensions, is in principle a 3 by 3 matrix. But because 2 of the elastic constants are exactly the same, you can make it a 2 by 2 matrix. And G is a 2 by 2 matrix. And G is D over no, it's the inverse matrix of D minus omega squared times the identity matrix, okay? And our boring material, our average material is going to be the standard isotropic Green's function and the standard isotropic dynamical matrix of an isotropic material. So we can just write down formulas for all those things. So this is a formula in terms of frequency-dependent lambda and frequency-dependent mu. And you take these two by 2 matrices, and you multiply them together, and then you take their trace, and then this d to the d cubed becomes q to the d minus 1 times some sphere times blah, blah, blah. And you can do the integral. You can do the integral. And there are 2 h's, and I haven't told you how to decompose it into lambda and mu pieces, but Stephen can tell you if you're interested. And so we can now oh, please, yeah.
What is jamming then?
Say again?
What do you consider jamming in this situation?
Okay, so jamming, oh, nuts. I was going to have a figure. Did I have a figure of? I never put in that figure, so let me write it down. So in this lattice, there's P, we'll call it P sub mu, and, sorry, P sub lambda and P sub mu. This isn't quite what they had. They had a bulk modulus and a shear modulus. Or no, they had the hexagonal bonds, or this would be P hexa in the original, and this would be P triangle. And this is 1, 0, and 1. So you know that up here where almost all the bonds are there, it's rigid. Where almost all the bonds are gone, it's floppy. You know that there's a certain number of bonds that if you dilute, it goes floppy. That's where the number of bonds is twice the number of atoms in 2 dimensions, okay? Except we're doing 3 dimensions, so it's 3 times. So there's a line in this diagram where it's isostatic. Right? And so that's the boundary between floppy and rigid. And along this line, you have rigidity percolation. That whole line is rigidity percolation. And what the clever lattice calculation did was this point, underneath it, the bulk modulus was 0, and above it, the bulk modulus was equal to 1. Okay, it jumps as you cross here. That's jamming. And the shear modulus grows linearly. And along, but the shear modulus is growing because I'm adding mu bonds. And so this is going to be the jamming point, and this is going to be a line of rigidity percolation points leading to jamming. Thank you.
Right.
Important question.
This is in the lattice, but the continuum case, I'm puzzled by what you're calling the...
Yeah, well, the continuum case, if you replace this with p lambda and p mu, it's the same. We're making it the same. P lambda says, the probability that I don't punch a hole, I replace it with by the original modulus, and P mu is the probability that I didn't punch a hole in the shear modulus. Yeah, yeah.
Just to make sure I understand the picture, are you looking at the P at which the effective, the bulk modulus of the effective spring or the effective sheet goes to 0?
Yeah,
Okay.
right.
So there's only one hole or one bond, and we're looking at this effective one hole.
We're doing a self-consistent approximation that has this transition. And if I punch holes, if I really think about physically punching holes, and I punch them in some ways, it won't have that transition, but it correctly describes a lattice which has to have the transition if you remove bonds. Yeah. Okay. Okay, yeah, yeah.
I have another one.
Yep.
So, in the
This
lattice,
is good. This is good. Yeah.
it's still clear to me in the lattice, but in the continuum limit, where you have an effective continuous piece,
Yeah.
which you're replacing, I don't understand why they couldn't theoretically overlap.
That's just what I was saying a moment ago. I keep thinking, so what happens when the holes overlap? And maybe I'll make fuzzy holes, but then the elastic modulus will never actually go to 0. And I'm agreeing with you that the intellectual foundations of our trick are kind of feeble, but it makes the calculation so much simpler, and I'm willing to cheat. Okay? And Danilo thinks I'm not cheating, and I haven't figured that out yet. But there's some summation over diagrams that leads to self-consistent equations that works. But it's certainly true. Say, I've been thinking about taking this and replacing it with a Gaussian hole, and then you can do the integrals also, and you get the same kind of self-consistent relations. And then I think, what happens when two Gaussian holes overlap? But that's all the kind of thing that CPA ignores, right? You don't pay attention to the limit where any two things are strongly interacting. That would be a different set of diagrams. Yeah.
When you compute the dynamical matrix in the isotropic material,
Yeah.
you set lambda, and what about the new variable?
So you remember that there were formulas from elastic theory for the dynamical matrix. And you multiply, you subtract I omega squared times the identity matrix, or I omega gamma times the identity matrix, and inverse that, and that's G. Okay? And those formulas I'm going to use in here. That's all I'm doing. Okay? And it's the thing about mean field theory that you are kind of allowed to cheat. That you're not accurately mimicking the real thing. And if you get the wrong answer, you can't complain because you didn't do the right thing. But often you get the right answer because life is simple. Now you could say, it's not usually simple when you have disordered systems. Maybe we have the wrong answer, but it's worth trying. Yeah.
I mean, in my experience, you have this age function. It will depend the kind of bond event. Like you may have like more like chain or flexible chain. I mean, when you have like the percolation, but there you, I'm not quite understand your dynamic matrix. It's why is 2 by 2? Because you are.
It's a 3 by 3 matrix in 3 dimensions. Isn't that right? Oh, it has to do with the number of modes, or it has to do with the number of. Pardon?
So given Q,
Yeah.
it's a 2 by 2 matrix in 2 dimensions, or D by D.
It's a D by D matrix, yes. There are 2 transverse modes and 1 longitudinal mode, but because it's isotropic, the 2 transverse modes are exactly the same, and so you can end up just having a 2 by 2 matrix. It doesn't matter if it's a 2 by 2 matrix or a 3 by 3 matrix. It's just a bunch of matrices that we're going to take the trace and then write a formula on the next slide.
But in the case of the lattice model,
The lattice model has 2 kinds of bonds, and so it's a 6 by 6 model.
it's a 4 by 4 matrix.
4 by 4 matrix for that, because it's got 2 kinds of bonds. Okay? And here we have 2 by 2 matrices, one for alpha equals lambda, and one for alpha equals, mu, and one for alpha equals lambda. Okay. Now I'm going to write down for you Steve's mean field equations. Oops. There it is. Oh, yes. Here we go. What am I going to do? I'm going to write down the self-consistent equations that you do by doing the integrals. And you remember, that was step 1. We found the mean field theory for the Curie-Weiss law for magnetization above 4 dimensions. And it made predictions that looked like this. They were nice predictions. And some of them are correct, and some of them are sort of okay. They does a pretty good job. But below 3 dimensions, it gives their own critical exponents. And above 3 dimensions, it's also only perfect in certain limits, in particular very close to the transition. So this is a mean field theory of jamming, but it's not guaranteed to give exactly the same answer as anybody else's mean field theory of jamming, in particular the infinite dimensional calculations. It would be nice if we could say, hey, you guys in infinite dimensions, see if you can generate this. And this isn't the answer. This is a calculation that the fussy details in it will matter. But whatever it is, you take mu over mu1, you get a relation which is p mu, the probability of punching a hole in, not punching a hole in mu, with this function on the right-hand side, plugged in for h. All right. So you might say, I'd like to have it simpler than that. And I'm saying, well, I'd like to have something that I was guaranteed didn't have any corrections to scaling that wouldn't be trustworthy. And we're hoping to get Mathematica to do these calculations, but so far Steve does them by hand. Okay. Now we have to step 2. The next 3 steps I'm going to just zoom through. The first one in the Curie-Weiss law, we shifted to Tc minus T. That becomes P lambda is 1 minus delta J. P mu is delta RP plus 2 plus delta. So this is that straight line here. We're measuring delta RP is the distance to that line, and delta J is the distance to this line. Good? Then we substituted, we cheated, right? We substituted what we had figured out beforehand was the right critical exponent for m, and the right combination of t's that describe the scaling behavior of the field, and we substituted the critical exponents we knew. This is not a practical tool. You have to go to some effort to figure out how to do this, but if once you know it, then you can plug it in just like you can take a derivative of a function that and prove that you integrated it right, okay? And so we plugged these in. We plugged in, so lambda, the bulk modulus, which is the part of lambda, jumps at the transition, so it doesn't scale with the distance to the transition. It goes as delta RP to the 0. Mu at the jamming transition scales linearly, so mu over mu1 is capital mu, which looks a lot like a capital M, times delta RP. Omega has omega over omega naught is delta RP times capital omega. And this complicated mess, Steve figured out if you use that for omega naught, it makes all the algebra simple. And then I have 2 other variables. One is a natural one. This is saying delta J over delta RP is measuring this over this. And we rescaled it by lambda 1 over mu 1. So that's W is basically the ratio of the 2 deltas. And then this funny guy, you remember somebody was asking, what was Z mu now that I don't have a lattice? And I say, we don't know what to call it. We just leave it Z mu. And Z lambda, by the way, turned out to be 1. So we only have one of the Z's left. And we're going to leave that in there. It turns out we needed that. And that'll be our dangerous irrelevant variable that we'll talk about in a moment. So we substitute these guys. We keep only leading order terms in delta RP. And even Mathematica can do the algebra after that, okay? So here's the self-consistent relations that we get out of that. So lambda can be written in terms of m and w and omega and things like that. And then m satisfies this equation. I keep trying to write it as m, plus or minus, by the way, are on the 2 sides of the rigidity of this transition, okay? So on the floppy side, it's minus, and the rigid side, it's plus, I think. And so the M formula, anyway, if I solve these 2, I'm done. Okay. Everyone good so far? Now, let's call this a dangerous irrelevant variable. Oh, good. Yes?
In your self-consistent equation, there are two parts of the division. I can't get it. Your first equation,
Yeah.
there is the state divided by 1 divided by 1. Two terms divided by 0, man. Look at it. Yeah, this is the numerator, the denominator is.
There are two logs. Say again?
Oh, I think I see what you're saying. You have log of that over that over that. That's what he's trying to understand, the divisions that you have there.
Yeah. You take this ratio,
It's the whole thing.
you
over
take its
the
log.
square root of n.
Yeah, okay, okay. You were actually mentally trying to figure out what this equation was. That's very interesting. Okay. When I see an equation like that, I say, thank you. And good. Okay. Now, Danilo in the supplemental material or appendix to JAMP? Supplemental material has this solution that he intuited numerically, and so he found the solution for z equals 0. I said that z was an irrelevant variable. Tradition is if it's irrelevant, let's set it to 0. And you get these nice equations, and you can actually solve these equations. Is this the solution? Yeah, this is the solution. Here's m, here's lambda, and here's the answer. That if you have plus, then as omega squared goes to 0, you get capital M going to a constant, which is 1, which makes mu go to 0 linearly, because you remember mu was m times delta RP. If you're on the negative side, the shear modulus, these two guys cancel, and as omega goes to 0, you get no imaginary part. It goes to 0, which is good because it's floppy. But even then, if omega is not 0, you get a frequency dependence. You get the right frequency dependence. Lambda has a different structure because, of course, it has a jump. So here's the solution for m. The real part of the solution goes to 0, and the imaginary part of the solution is absolutely 0 until this point, and then it pops up. Okay? And this is for m plus. And this is lambda plus on the rigid side, and it has a real part that goes into a constant as you go down as you go to omega equals 0, and it in the light gray the dim version, that's z equals 0. It has a cusp as well. Now, "45 more minutes. I'm almost done here, so we may have a nice lunch. Unless you have more questions. So what are these other curves? What are the dark curves? Well, it's a little weird to have no dissipation. There's no bulk dissipation. There's no shear dissipation all the way up to omega is, this capital omega is 1. Those of you who know about jamming, they have a little omega star, which goes to 0 at the jamming point, and you have this constant density of states. So the density of states, as a function of omega. This is the number of phonon modes there are as a function of omega, and it typically looks something like this, and there's omega star. And capital omega, and this thing goes like delta z, and this thing corresponds to capital omega equals a constant, say 1. So this big bulge in the, I'm sorry, I drew that wrong. I'm doing the boson peak. It goes like this. It goes to a constant. You remember it went to constant and it kept going down in Professor Urbani's lecture. So okay. So I haven't derived for you this density of states, which is one of those universal scaling functions that you get by plugging in the right, these frequency-dependent elastic moduli into this big table. But it'll look like that. Now, I was saying, though, the imaginary part here goes to 0 below omega star, below capital omega. There's no reason why a phonon with this frequency should not scatter at all off the dirt. We know that's wrong. So there's something about the variable we left off, z, or at least something that we've left out of the theory. But z is a natural culprit, right? That we kind of needed z to make everything work. And when we set it to 0, we're getting something that's got the wrong physics. So let's see what happens when we add z. Now you remember that adding z isn't trivial. We wanted to solve a self-consistent equation with a logarithm involving z times z. We're still thinking about how to do that effectively, but you can trust that we just did it. We just found the self-consistent solution. Actually, we didn't. Stephen found an approximate method for getting it, and I've forgotten why we never put it into the slide, but there's so this is what happens when you make z is 0.1. So z is an irrelevant variable. It's going to 0 when you get close to jamming. 0.1 is sort of close to jamming, and sure enough, no longer do you have 0 imaginary part. You've just got a small imaginary part, which is probably the right physics. Okay, so there were two things about a dangerous irrelevant variable. Something was completely wrong. So if I call this the damping, you may say, well, that's not completely wrong. It's pretty close to 0. But if I call it the attenuation length, that's going to infinity. Okay? So I really need z to keep that physical. And the other rule was that the universal scaling function could not be Taylor expanded. We cannot solve the self-consistent equations in the previous slide by doing a Taylor expansion in z. It didn't work. I should have known it wouldn't have worked. I spent a long time trying. This was probably 3 weeks ago. And we finally recognized that it was doomed. We solved the self-consistent equations, and then we came back and found a sneaky way to do it. But it's non-analytic. I mean, you can tell, because here there's a linear, as you change z, it changes linearly. But near this cusp, it suddenly changes in a very different way. It changes in a way that's not an analytic Taylor series. All right? We're getting near the end. Any questions? So we got a dangerous irrelevant variable, a crossover, a singular correction to scaling. Yeah.
I'm still a little bit confused about the delta rigid percolation in this 3D case. I understand that has to do with the diagram. But then why is it irrelevant? In the sense that it seems to me to be a distance to somehow a value.
Why is what irrelevant?
Yes. Why is Z irrelevant? It depends on
Okay. So what Professor Rita is asking, this capital Z, we defined to be, whenever we saw Z mu, we stuck this in. And you ask, where did that come from? Why is capital Z so important? And, okay, so it's typical for irrelevant variables to be mysterious. Okay, you have some critical point and you find, oh yes, it's unless I tune field and temperature to the critical field, the critical temperature, I don't see the critical behavior. So I know very well those two. So my model has those two things. Ising model has a bond strength that sets a critical temperature, and it's got a strength of the external field. And so I know those two parameters are in my model. If I want the leading correction to scaling, I don't have any other parameters. I can't vary it. It's there. It's got a value, but it's not a value I can see how it changes things if I change it. So typically you add another feature to your model. You add something, here's an Ising model of the next neighbor bond. And then you can tune the next neighbor bond and you can see the irrelevant correction to scaling move up and down. Sometimes you make the extra bond perfectly set to make the correction to scaling go away so you can get better critical exponents. In our theory, previous slide, there are only two things. There's Q Debye, and then there's this stupid Z. Where did Z go? There's a Z someplace. There's the Z, okay? And there was this log term, and the powers didn't balance inside that log term. Let me back off. Okay, what we really found is that Steve would do the simulations and the self-consistent equations with the integrals, with that original bond lattice, had dissipation, and Danilo's universal scaling form didn't. They had the rounding. And we were looking for that, and we wanted to keep something new, and it went away when you got closer and closer to the critical point. When you went closer, so it looked like a correction to scaling. It looked like a dangerous correction to scaling, a dangerous irrelevant variable. So we were poised to look for something to tune. So to say again, the solutions to the integral equations look like the dark curves, right, the smooth ones. And the solutions to Danilo's equations had this cusp. Danil's equations were a triumph, but it had this weird feature that we didn't see. And so he would get closer and closer to the transition, and it was really hard numerics, and it drove him crazy, but this kept getting smaller. And so we knew that Danil was correct to leading order in some sense, but we knew that this cusp wasn't something that was just a regular correction to scaling. It was a dangerous, irrelevant variable. So we were motivated to keep going. Otherwise, why bother? They've got the answer in the supplemental material. We don't need to do another paper. And that led us all into trying to do the isotropic theory, and we found this feature in rigidity percolation where we couldn't get it in jamming, and so we did the isotropic lattice step by step by step. But I'm not saying that Z is some really special thing. It's just a parameter like the next neighbor bond. Where did it go? This Z is like a parameter like a next neighbor bond. It's something I have a handle that I can move. If I had a different model that didn't have a Z but had another bond or something, it's any other parameter in the model that you aren't using for the relevant directions, you can use to vary the dangerous irrelevant one. Now, I should say that Steve and Danilo and I have been asking that question too. And it wasn't until you asked the question that I came up with that answer. So thank you for asking that question. We'll have to take notes and stick that in the paper, if you believe me. Yes, good? Okay, so we have our self-consistent solutions. We have our dangerous irrelevant variable, and the final slide, only half hour early, no, I'm sorry, we have another. You remember, I claimed I'd describe jamming, and I claimed I'd describe rigidity percolation. To be frank, we got the rigidity percolation a long time ago. It was the jamming point that was driving us crazy. But anyway, using this jamming point, we just look in the neighborhood of this line, and we should get rigidity percolation. That's the rule, that you look at the multi-critical point that's unstable in the renormalization group to the lower order critical point. And the multi-critical point has to have the singularity appropriate for the jamming point has to have a scaling function that includes the singularity for rigidity percolation. All right, so what we do is we change variables to the variables appropriate for rigidity percolation, where instead of taking delta RP to the 0, we're going to multiply by delta RP, and this is all lambda 1 for rigidity percolation involves these constants. And then W, which you remember was the ratio of delta J to delta RP. When delta RP goes to 0, it goes to infinity. We can take our formulas and take that limit, and then we get the universal scaling function for M being the same as it was. The universal function for lambda bar is just exactly the same as the universal scaling function for M. You might think, that's weird, but Stephen has been telling forever, rigidity percolation always has the two being exactly the same except for an overall constant, because there's only, in the triangular lattice, there's only one bond, and it has some frequency dependence, and both lambda and mu have to inherit that frequency dependence. So this is this picture we had before is exactly the same as the picture for rigidity percolation, except now it works for both lambda and mu. Okay, so that completes our scaling analysis, and I just wanted to emphasize that there are lots and lots of predictions for this theory, some of which have not been ever measured in the real jamming simulations, in the real rigidity percolation. One of the things that everyone looks at in jamming is this plot. And we didn't have time to generate this plot, although we figure out how. But this is the correlation function, which also has what we call the boson peak. Okay? That the correlation function, that formula in the last lecture, if you just plot it as a function of capital Q and capital omega, has this giant bump that corresponds to having lots and lots of low-frequency phonons. Our model for those phonons are damped harmonic oscillators. The real phonons are doing this incredibly intricate local non-affine deformations. And it'll be a miracle if it all works, but sometimes miracles happen. And I'm looking forward to somebody doing a real numerical test. But we predict the power law dependence with omega and with wave vector. We have this boson peak. And this is the kind of thing that if we can make it work, will be the emergent theory on long wavelengths, apart from the avalanches, apart from the nonlinear aspects. Thank you very much.
Okay, questions? I do have a question, Caroline, I asked you about the P lambda and P mu diagram and the generalization from the lattice to the continuous model. And you had this nice idea of comparing this, or a nice way of thinking about this when you make contact, for instance, with the tuning by pruning idea that Carl and Andrea and Sydney did some time ago. So maybe you can comment on that, and maybe it will be clear then.
So maybe you could comment on it. This is much more your work than mine, but Andrea Liu and Carl Goodrich and succeeding graduate students whose names I don't remember have been looking at how to take a lattice, disordered lattice, snip some bonds, and change the ratio of the elastic moduli. And this is called tuning by pruning. And they started out by very carefully finding which bond would make the bulk modulus change the most, or which one would make the shear modulus change the most compared to the bulk modulus. And by picking out like rather few bonds, they could completely change the overall shear modulus. Danilo in it's another paper, right? With Lubensky and Xiaoming and other people, took that and didn't do a careful job. They didn't carefully pick the next bond to move. They just had a lattice and they would remove one kind of bond or the other kind of bond and drew a phase diagram of shear moduli. And if they picked two kinds of lattices to glue together, one of which had a bulk modulus and no shear modulus, and the one of which had a shear modulus and no bulk modulus, or something like that. And I'm being vague because this is Danilo's work and not mine. Sometimes I'm vague, even though I'm an author. This one, I'm not an author, okay? The first one, I'm not an author. Then they could also get any Young's modulus and shear modulus by getting very close to these special transition points. And in a sense, our calculation is just taking that and turning it into a scaling theory for the jamming transition. It's a nice connection. Thank you, Mark. Oh.
It's not for the continuous.
Say again?
What you explained is the works for the network, for the lattice.
Yeah, I think the idea is that the P lambda you can interpret as you're making holes in the continuous model, but of a different type of bonds, for instance. And the P mu would be the other one. The one that affects the shear modulus and the one that affects the bulk modulus, for instance. That's the connection.
Thanks for coming. You've been a great audience. I've really enjoyed being here, and have a good week.